If looking at 3D geometry problems makes your heart race, you are in the right place. Complex spaces can overwhelm our visual processing, but we don't have to solve everything at once. We are going to take this messy 3D shape, straighten it out, and untangle it into simple, flat, two-dimensional pieces. Looking at this specific homework image, we can clearly see our objectives. We have a 3D solid cube, and the prompt asks us to find the exact length of three distinct segments: CF, AC, and EC. This diagram shows the core mathematical tool we will use to find those lengths, the Pythagorean theorem. Remember, for the formula a squared plus b squared equals c squared to work, c must always represent the hypotenuse, the longest side directly across from the 90-degree right angle. Let's orient ourselves to the 3D space we are working in. The wireframe has a distinct back wall, a front wall facing us, and a flat floor connecting them along the bottom. The prompt gives us a very clear starting parameter. Every single visible outer edge of this shape is exactly 2 inches long. Before we calculate anything, we have to address the perspective illusion. When a cube is drawn in 2D space, the internal angles look slanted or stretched out. However, because this is a perfect cube, every single corner is a precise 90-degree right angle. By trusting the geometric rules rather than our eyes, we know that this shape is packed full of flat, perfectly solvable right triangles just waiting to be extracted. This image highlights our first target, segment AC. You can see it acting as a diagonal line stretched directly across the back wall of the cube. To make the math manageable, let's grab that back face and literally pull it out of the 3D space. Once it faces us directly, it is just a simple, flat square. Inside that square, we can isolate triangle ABC. We know the outer edges of the cube are 2 inches, which means the two legs of our right triangle are 2 and 2. Plugging that into our formula, we get 2 squared plus 2 squared equals our hypotenuse, c squared. 2 squared is 4, and 4 plus 4 gives us 8. This means the hypotenuse squared is 8. To get the final length of segment AC, we take the square root. For now, leave the answer as the raw square root of 8 to keep the arithmetic straightforward. Moving back to the full wireframe, our next target is segment EC. This line operates as the diagonal cutting across the flat floor of the cube. Because this is a perfect cube, the floor shares the exact same geometry as the back wall. The triangle on the floor also has leg lengths of 2 and 2. That mathematical situation is identical to what we just solved, meaning segment EC is also the square root of 8. Solving face diagonals is just flattening one side of the cube at a time, turning a scary 3D problem into a basic 2D problem. This diagram shows our final and most challenging target, segment CF. Notice that this line does not trace along a wall or a floor. Instead, it cuts straight through the empty internal space of the cube. To find its length, we must build a triangle inside that empty space. This animated model highlights internal triangle FEC. Because it sits at a harsh angle, it looks highly unintuitive at first glance. Despite how it appears, angle E is a perfect 90-degree right angle. The edge FE is a vertical wall, dropping perfectly straight down onto the flat horizontal floor represented by line EC. Where a true vertical meets a true horizontal, a right angle is formed. We already know the dimensions we need to solve this. The vertical leg, FE, is an outer edge, so it is 2 inches long. The base leg is the floor diagonal we just calculated, the square root of 8. Grab a pencil and pause here. Try setting up the Pythagorean theorem for this specific triangle. If putting a square root into the equation feels strange, ignore that feeling and just follow the strict formula. Let's set up the math. Our first leg is 2, so we start with 2 squared. Our second leg is the square root of 8, which we will place carefully inside parentheses before squaring it. All of this equals our hypotenuse, CF squared. When you apply a square to a square root, the two algebraic operations simply cancel each other out, leaving only the whole number inside. So the square root of 8 squared is just exactly 8. That makes our arithmetic very clean. 2 squared is 4 plus 8 equals 12. Taking the square root of our total gives us the final length. CF equals the square root of 12. Solving a complex 3D space diagonal requires identifying a flat surface diagonal first. Once you have that measurement, use it as a base leg to solve the internal triangle. Excellent work! You took a complex, intimidating 3D shape and systematically broke it down into flat, familiar pieces. This cheat sheet provides the final solutions for the homework assignment. The length of AC is the square root of 8, EC is the square root of 8, and the internal diagonal CF is the square root of 12. Depending on your math professor, you may be asked to simplify those final values. If you do, the square root of 8 simplifies to 2 root 2, and the square root of 12 simplifies to 2 root 3. Either version is mathematically correct. Your assignment also asks for a brief written explanation. You can summarize it like this. To find an internal space diagonal, you must calculate a face diagonal first, because it acts as the base leg for the internal space triangle. When you encounter 3D shapes on future exams, pause, ignore the clutter, and just look for the flat right triangles hiding beneath the surface.